Greetings once again, and welcome to another video on the topic of quadratics. So still on pure chapter 2 of the algebra book, and we're going to have a look in particular today at modelling with quadratics, which is a huge new area of the course. So not only is this a pure topic, modelling with quadratics, but it also ties in hugely to the mechanics side of the course as well, where we model projectiles as quadratics, because as you'll see in the mechanics side, a particle or projectile will fall under gravity with a parabolic curve, which is very interesting indeed. So this topic here has links in loads of places, and so this is why we're going to spend quite a lot of time with modelling with quadratics. But before we come on to that, I've got a few warm-up questions for you as ever. So 4 warm-up questions here, and so pause the video now and try them yourselves. Once you're ready to see the solutions, play the video and just double check that your solutions match my own. So let's have a look together at the solution to question 1 of this warm-up activity. So we're told here that the minimum value of this quadratic is y equals 20 when x equals 3. We're asked to find the value of y when x is 4. So the important thing we need to remember from what I mentioned in the last lesson is if a quadratic is written in this form, the completed square form, then it tells us essentially what the turning point is. So the turning point can either be a minimum or maximum. In this case, it's a minimum. So we're told that when x is 3, that relates to this a here, that y is 20, and that y is 20 relates to b. And so we can substitute these values in, and we can deduce, therefore, the equation of this quadratic is actually x minus 3 squared plus 20. Okay, because we're told that when x is 3, y is 20 at this turning point. So now we know this equation, we can then substitute in x equals 4. So if you just sub now x equals 4, we get that y is going to be 4 minus 3 all squared plus 20. 4 minus 3 is 1, so 1 squared plus 20 is just 1 plus 20, which is 21. And so we now know that when x is 4, y must have a value of 21. Question 2, we need to use the discriminant idea, which we mentioned last lesson, to prove that this equation here has no real solutions. The first thing to notice is this equation here isn't in the standard quadratic form. We need to rearrange this, and so the right hand side is equal to 0. And so if we subtract 2x from both sides, we have x squared plus 4x plus 8 equals that 1, which is now on its own. Then subtract 1 from both sides, x squared plus 4x plus 7 equals 0. Now the discriminant is b squared minus 4ac, where a, b and c are the coefficients of x squared, x and the constant term respectively in the standard form of a quadratic. And so in our case, b is 4, a is the coefficient of the x, which there's only 1x squared here. So if we imagine an invisible 1, a ghostly one, don't mean to scare you. So a is 1, and c, the constant term, is 7. And so if we just substitute in these values, we see that the discriminant must be 4 squared minus 4 times 1 times 7. 4 squared is 16, 4 times 7 is 28, so 16 minus 28 gives us minus 12, which is less than 0. Now when the discriminant is less than 0, that's a proof that the quadratic has no real solutions. And so we've done it there by just using this property of the discriminant. So we can now move on to question 3. Question 3, we're told that we've got these two expressions with the same minimum value, and we're asked to find the value of a. Now, the minimum value, the turning point, we can work out by completing the square for both expressions. And so if I just take this first one here and manipulate this into vertex form, which is what I sometimes call the completed square form, we can rewrite this as t minus half this coefficient here. Half of minus 4 is minus 2. Square all of that. Subtract away the minus 2 all squared, which is minus 4. Then finally this plus a. And so this one will have a minimum when t is 2. And when t is 2, this bracket is equal to 0. So we just have minus 4 plus a. And so that minimum value for y is this. Meanwhile, we can do the same for t squared minus 6t plus 8 and complete the square on this. So if we just take this one here, we'd have t minus 3 all squared minus the 3 squared, so minus 9 plus 8, which we can simplify ever so slightly into t minus 3 squared minus 1. And that has a minimum where t is 3, and when t is 3, this whole bracket and the square of it is 0, and we just have minus 1. So the minimum value of y for this one is at minus 1. We are told, though, that these have the same minimum value. So from these two bits here, we can see that this minus 4 plus a, because it's the same minimum value, that must be the same as minus 1. So now we can quite easily rearrange this by adding 4 to both sides, and we see that a has to be 3. And so that's the trick for that one. We can complete the square for both of these expressions. Finally, for the warm-up question 4, we've got 3 different parts to this, and we have a diagram showing a graph of y equals x squared plus px plus 5, whatever p may happen to be. P and q are non-zero constants. So for this particular question, we don't need to worry about q. Q doesn't actually exist, so in fact, come to think of it, I don't know why I've included q, but forgive me, we're just interested in p. So we need to write down the value of y when x is equal to 0. So what I'll do first of all here, actually, I'll just get rid of that q. It's a slight aberration. Apologise for this. P is a non-zero constant. There we go. It never happened. So what's the value of y when x is equal to 0? Well, when x is equal to 0, all of this here is just 0. X squared is 0, px is 0. We're just left with 5. And so when x is 0, y must be 5. So that here must be at 5. Part B, without using a calculator, write down the value of the discriminant. So just remember, the discriminant is b squared, which in our case is p, minus 4 times a times c, where a is the coefficient of x squared, which is just 1, and c is a constant term at the end, which is 5. And so the discriminant is p squared minus 20. For part C, calculate the exact value of p. Well, if we look here, we can see that this curve only meets the x-axis in one particular place. So it's just got one repeated root. So because we can see it's got one repeated root, that tells us that the value of the discriminant must be exactly equal to 0. That's a key property of a discriminant. If it's got one repeated root, the discriminant's equal to 0. If it's got two distinct roots, the discriminant is greater than 0. No roots, the discriminant is less than 0. And so based on this now, this discriminant, p squared minus 20, must be exactly equal to 0. We can now rearrange this into p squared equals 20. So if we square root both sides, we get initially that p must be plus or minus root 20, which is a third with 4 as a factor. So this can simplify into root 4 root 5, but root 4 is 2. So that's the same as plus or minus 2 root 5. So it's tempting initially to think, well, there's two possible values of p. However, if we look at this graph, the minimum value is where x is a positive. Okay, so because of that, what we have to pick here is that p is actually negative 2 root 5. And I'll show you why. And so here, if we have negative 2 root 5, this becomes x squared minus 2 lots of root 5, x plus 5. If you complete the square on this, we'd get x minus root 5 squared, minus off root 5 all squared, which is minus 5, plus 5, which just becomes this. So this has a minimum value where x is positive root 5. If we picked this positive value of p plus 2 root 5, this would have a completed square of x plus root 5, which would have a minimum point where x is negative root 5. So actually we need this negative root here, so this negative value of p. If we pick the positive value of p, the quadratic could be over here like this. So from the graph, we can see that actually p has to be negative 2 root 5. So we reject the positive option. We can now start having a look at modelling with quadratics properly. So let's move forward, having done the warm-up. Just to remind you what I quickly mentioned last time, a quadratic function can be written in two key ways. Apart from the standard form, ax squared plus bx plus c equals 0, we can always write it in the completed square form, which I'll sometimes call the vertex form, where y equals capital A, brackets x minus h, all squared, plus k. That will have a turning point, either a maximum or a minimum, where x is h and y is k. And so this form of the quadratic allows us to easily see where the turning point is. If the quadratic has at least one solution, we could write it in root form, which is essentially just a factorized form of it. If it's got two roots, the quadratic can be written like this, where a is some multiplicative factor, some multiplicative constant, or if it's got one repeated root, becomes this here. Now, if it has no roots, we can't factorize it, and so the root form can only be applied when the quadratic has roots. So depending on the question, each form has its own pluses and minuses. The vertex form is useful sometimes and not as useful other times, vice versa for the root form, which is the factorized form. So let's have a look at a few examples. So first of all, we'll look at example 1, modelling with quadratics. So we have this graph, y equals ax squared plus bx plus c, where a, b and c are non-zero constants, and we're told it has a minimum value when x is 5 and y is minus 3, and also that it passes through the point 4, 0. Find the values a, b and c. So just a reminder before we start, we've got these two main forms for the quadratic. But we are told in this question what the minimum is. And so because we're told what the minimum is, we can use this completed square form to make things easier. So in our case, the minimum is where x is 5. So this h value is 5. The value of y at the minimum, k, is -3. And so we can just hijack this and use it to our advantage. So subbing in that h is 5 and y is -3, we can say that y equals some constant a. This might be 1, we don't know yet. X minus 5 all squared minus 3. Luckily for us though, we're told an extra point. We're told it passes through for 0. So based on this, we can now sub in that x is 4 when y is 0. Or y is 0 when x is 4, whichever way you want to think of it. So now what we'd have is that 0 equals a brackets 4 minus 5 all squared minus 3. So let's neaten this up. So 0 equals a minus 1 all squared minus 3. Minus 1 all squared is just 1. So this is 0 equals a minus 3. So therefore a equals 3. Just going to give myself a bit more space so I can seal this on the same page. So because a equals 3, we therefore have that y must equal 3 lots of x minus 5 all squared minus 3, because we've worked out now that a is 3, so we can just swap out the a with the value of a, because a is 3. So that's the equation, or one equation at least, of this quadratic curve. However, the question asks us to find the values of a, b and c, so it's written in this standard form. This form here is different to what we need, so what we need to do now is expand this out. So expand out the brackets. So x minus 5 all squared is x squared minus 10x plus 25, and then that minus 3 on the end. So multiply all of this by 3, we get 3x squared minus 30x plus 75 minus 3, which we can then make simpler by saying it's 3x squared minus 30x plus 75 minus 3 is just plus 72. Now that form is more useful. So comparing the coefficients of x squared, a has to be 3. Comparing the coefficient of x with b must be minus 30. And comparing the constant term c, we can see c is 72. So we've done the first worked example. Worked example 2, we can model the path of a rugby ball, this is true by the way of course, through the air as a parabola in the vertical plane. The vertical plane just means if you had an imaginary vertical sheet like a see-through pane of glass, the rugby ball would be moving in a two-dimensional plane where it's just moving up and down, not side to side. In real life it might be of course because of the wind, but we can just model this as being a two-dimensional plane going straight up and straight down when it comes down. So the ball hits the ground for the first time 20 meters from its point of origin. The maximum height of the ball along this path is 8 meters. Assuming the ball is kicked from the origin, find an equation for the path of a rugby ball in the vertical plane. We now have actually 2 different options for working this out. You can use either the vertex form of the quadratic or the root form, depending on what you find easier. Personally, I think for this case, factorized form will likely be easier. So let's just add in a few bits and pieces to this diagram. Okay? So first of all, we're told that it's kicked from the origin. And so what we can do is we could superimpose a coordinate grid. like so. Okay, so that could be our x-axis, and this is our y-axis. So we can imagine it graphed like this. Now, we know the two routes. So we know that it crosses the x-axis here and 20 meters after. And so based on the root form of the equation, which I previously mentioned, the factorized form, we can say that y is going to equal some multiplicative constant a multiplied by x minus 0, because one root's at 0, x minus 20, because the other root's at 20. So just 0 and 20, that's where these numbers here come from. However, x minus 0 is just x, isn't it? So we can say this is the same thing as ax, x minus 20. But that's only going to take us so far, because we need to know some more information to work out what this value of a is, if it's 1, 2, 3, or a negative. I'm hoping you can have an educated guess that a has to be negative, because this parabola is bending downwards. Okay, it's a negative, it's an unhappy parabola, which you may have heard from GCSE, as a teacher explains it colloquially. So we need to find out what a is. So what we need to do now is think, whereabouts will this rugby ball be at its maximum point? Something important you need to get used to is that the turning point of a quadratic is always halfway in between the roots. So we have a root at 0 and 20. What we can now deduce is that this turning point of it will be where x is 10, exactly halfway between. That's slightly off, about there. And so what we can say is that this turning point will happen halfway between the roots, halfway between 0 and 20 is where x is 10. And we're told as well that the maximum height is 8. And so when x is 10, y must be 8. So we can add this into our sketch as well. So because we know the turning point, which is 10 and 8, we can sub this value in to this equation. So we know that y is ax, x minus 20. So let's now sub in the coordinates 10 and 8. So when y is 8, 8 equals a times x, and so that's a times 10. So we're going to put 10a brackets 10 minus 20. So all we've done in this case is just substituted in that when x is 10, y is 8. That's the only thing we've done. So this can now be neatened up. Okay, so we have 8 equals 10a times 10 minus 20. Well, 10 minus 20 is minus 10. 10 times minus 10 is minus 100. So 8 equals minus 100a. If we divide through by minus 100, you can then see that a must be minus 0.08. Okay, so the equation of a ball, we just substitute in now that a is minus 0.08. So an equation is y equals minus 0.08 x brackets x minus 20. And so that is the equation for this rugby ball. However, it's not actually the only equation. If you used a different way, if you went for the vertex form, you may have got this. So if I just scroll down, so in brackets, you may have got this. If you if you haven't got this, don't worry, this is fine. The main thing is you should have had one or the other. So in the vertex form, it would have been minus 0.08 x minus 10 squared plus 8. What I'd suggest you might want to do is to check on Desmos or some graphing software and verify for yourself that this equation here is exactly equivalent to this one down here. And so whichever form you've used, if it's one or the other, both of these would score you full marks if you arrived at either one of those. To finish off with, there's one final worked example, which is about a stone being thrown from the top of a cliff. So this particular stone is thrown from the top of a cliff, and we're told that the height, h, in meters of the stone above the ground level after t seconds is modelled by the function h of t is 115 plus 12.25t minus 4.9 t squared, where t is non-negative. T is equal or greater than 0. So for part A, give a physical interpretation of the meaning of a constant term 115 in the model. This is a very common 1 mark question in an exam, this type of question. So the constant 115 is just when this function is equal to 115. And so this function is equal to 115 only when these terms here are equal to 0. And these will be equal to 0 when t itself is equal to 0. And so 115 is the height at t equals 0. In other words, 115 must be the height from which the stone is thrown. So the height from which, that's a bit of a dodgy W, the height from which the stone is thrown is 115 meters. That's all it means. And typically the fact it's a 1 mark question, which it would be, is a giveaway and a clue as to the fact it's actually more simple than what it may initially seem. For part B, we need to write this function of t in the form a minus b brackets t minus c squared, where a, b and c are constants to be found. This here, because this is a squared thing, essentially what it's saying is we must complete the square for this expression. So first of all, let's just write down what h of t is in expanded form. And then step by step we can complete the square from there. Now when we complete the square, the coefficient of the squared variable has to be positive. So this currently is minus 4.9. So what we're going to do is factorise out this minus 4.9 from the equation. We can leave this 115 on its own actually, but for this bit here, let's just factorise out minus 4.9 to make the t squared part positive. So if we factorise out divide by minus 4.9, we get t squared, and then this here will become a negative. So this 12.25 will end up being 12.25 divided by minus 4.9. So let's see what this is on a calculator. So if we just were to do 12.25 divide by minus 4.9, we're going to get minus 5 over 2. So that's going to be minus 2.5. So that's going to become minus 2.5t. And so all we're doing first of all is rewriting this bit of highlighted in blue. It's going to become this. And this plus 115 can go on after. Next up, we can complete this. We can complete the square on t squared minus 2.5t. So we have minus 4.9 at the beginning. Then in brackets, t squared, we just rewrite this t inside the brackets. We half the coefficient of t. So half of minus 2.5 becomes minus 1.25. We square that, and then we subtract off 1.25 squared. So let's work this out. So 1.25 squared gives us, as a decimal, 1.5625. So subtract off 1.5625. So I'm just rewriting this part of the expression in this expanded form. Sorry, in this completed square form, I should say. And all of this is plus 115. We can now expand this out, so we can multiply everything inside these big squared brackets by minus 4.9, which gives us minus 4.9 lots of t minus 1.25 all squared. Then minus 4.9 multiplied by this value here, that's going to give us, minus multiplied by minus gives us a positive, so it's going to give us, as a decimal, 7.65625. So plus 7.65625 plus 115. Now, part B, we're asked to write this as the constant term first and then minus off the bit involving the t. And so we can combine the 7.65625 with 115 to arrive at 122.65625 minus 4.9 brackets t minus 1.25 all squared. And so that's now rewritten in the correct form. So for part C, next, it says using the answer to part B or otherwise. So it's worth just reminding ourselves what we got for part B just now. So part B, our answer was this, I've included here. So for part 1, we need to work out the time taken after the stone is thrown for it to reach ground level. So for part 1 of part C, what we need to realise, the time taken after the stone is thrown for it to reach ground level, when it reaches ground level, the height, which is h of t, must be equal to 0. And so what this means here when it says the time taken after the stone is thrown for it to reach ground level, that's just asking us to work out what the value of h of t is, sorry, what t is when h of t is equal to 0. So we are wanting to solve when h of t is equal to 0. So what is h of t? Well, h of t is this expression here. Or in a simpler form, h of t is this. So we can solve for this being equal to 0. So I'm going to show you one of two ways. One using a calculator, the first method without. So we need to rewrite 115 plus 12.25t minus 4.9t squared is equal to 0. We can now use the quadratic formula for this. So I'm just going to put in this bubble here using the quadratic formula. We can use the formula for this to work it out quite simply. So t is going to be minus b, which is going to be minus 12.25, plus or minus the square root of 12.25 squared, minus 4 times a, which is minus 4.9, times c, which is 115, and all of that is going to be divided by 2 lots of a, which is 2 times minus 4.9. And so if we calculate this now on the calculator, so we're going to have as a fraction minus 12.25, oops. Let's try plus first, so plus the square root of 12.25 squared minus 4 multiplied by negative 4.9 multiplied by 115. All of that divided by 2 lots of negative 4.9. So that's going to give us this value here, which is, as a decimal, minus 3.75, so we get t as a negative value, which doesn't really make sense. When t is a negative, that's before the stone is thrown, so we're going to reject this route here. So what's the second option? This is going to be when we have a positive square root. So if we just toggle back, if we change this positive sign, so we've tried the positive sign already, so let's try the negative option, the negative square root. So if we try minus 12.25 minus this square root symbol, so minus the square root of 12.25 squared minus 4 multiplied by minus 4.9 multiplied by 115 all over 2 lots of minus 4.9. Now that gives us, oh, we've got minus 3.75 already. Sorry, my mistake, I'm being a bit silly. So if I just alter off, I'm going to try this plus to a minus. That's what I meant to do. Apologies. So the time which it's at ground level is after 6.25 seconds, but we're not after the time. Actually, no, we are after the time taken after a stone is thrown for it to reach ground level. So it's at 6.25 seconds to 3 significant figures. So the stone reaches the ground after about 6¼ seconds once it's rounded off. For part 2, we want the maximum height of a stone above the ground and the time after which this maximum height is reached. So we're going to use this completed square form here. So for this, we just use this form of the equation. Remember, this is called the vertex form, which tells us the coordinates of the maximum. So it's going to be at a maximum when this expression here is equal to 0. And that's going to happen after 1.25 seconds. And so the time of the maximum height is going to be after 1.25 seconds. So it's at maximum height after 1.25 seconds. And after 1.25 seconds, it's at this height here, which is a constant term on its own. So we could round this off. If you're not sure what to round it to, always give it to 3 significant figures. So to 3 significant figures, it would be 123 meters. If you wanted to put it to 122.7, that's fine. If you wanted to leave it as it was, that's fine too, because the question is not said. But if you're not sure, give the answers to 3 significant figures. So what I'll do here, actually, I think I'll compromise and give it to 1 decimal place. So it's going to be a maximum height after 1.25 seconds, after which time this part of the expression vanishes, and the maximum height is going to be 122.7 meters. So maximum height is after 1.25 seconds, and the max height of this particular stone is approximately 122.7 meters, given to 1 decimal place. And that's all from me. What I'd like you to do now is to try exercise 2H, all questions on page 34 and 35 of the blue algebra book. So as ever, do the questions yourself, try to check your answers using the back of the book to see if you've gone wrong, or if you have, just use that to self-correct and see where you may have made a mistake. If you're not sure where you've gone wrong, either ask a classmate or just let me know in class, or send me an email, or even leave me a little message on this video. So thanks for listening and getting to the end of the video. If you have, keep working hard and please be in touch. Thanks very much. You'll hear from me again soon. Bye for now.